today's topic, logarithmic functions. We're finally getting there today. So our objectives: convert between logarithmic and exponential, evaluate log expressions, apply basic properties. We're going to graph a little bit, and then we're going to use some in applications. So once we discuss what this is, like, okay, how do we apply it? And they're seen everywhere. Okay, if you guys are in chemistry, you guys use it in chemistry quite a bit, actually, believe it or not. So to start us off, I have just a couple of just real quick examples down here I want us to talk about. So for the first one, what power does 2 have to get raised to get 8? 3, okay. 2 to the what power gives me 16?
4.
Okay. 2 to the what power gives me 32?
5.
2 to what power gives me 10?
1/5. No.
Nope. We're stuck, huh? Now, we could probably make a guess.
3.
So it's going to be between what, 3 and 4?
Yeah.
We kind of agree with that? Okay, so it's going to be maybe some decimal value. But yeah, we're kind of stuck. So what do? Well, we solve for x, huh?
Yeah.
How do we solve for x? That's what it comes down to. So here's the deal. 2 to the x, that's an exponential function, right?
Yeah.
So is that a 1-to-1 function?
Yeah.
It is. Pass the horizontal line test, right? If you look at it graphically. So it has to have an inverse, huh? So what's the inverse to an exponential? That's what we're going to look at today. Okay? So let's talk about that. Okay? So here is the exponential equation, right? And I want to find the inverse of it because that's going to help me find 2 to the what power gives me 10, right? So to find the inverse, we know that we have to first let that be y, right? Then we switch the x and y, so x equals b to the y. Okay, and we're done. There's really not much further I can go with that. This right here is our inverse for exponential functions. Okay. Now we have a different way of showing what this is. Okay, so this is the same thing as me writing. I'll show you. Okay, y equals log base b to the x. Okay, we call this a logarithm. So essentially, okay, what input value is going to give me the exponential with that exponent there? Okay, so this is going to undo our exponential functions. Let's write a formal definition for it. If x and b are positive real numbers such that b is not 1, then y equals log b to the x is called the logarithmic function base b, where y equals log b to the x is equivalent to b to the y equals x. Okay? So there's our formal definition. Okay? Yes?
Is that superscript x or just an x?
The x is next to the log part. So b
Okay,
is
so it's the same level as log.
yes, correct.
Okay.
Absolutely. Yeah. Now, here's the deal. Why the word logarithmic, right? It seems kind of an arbitrary choice. That's a problem I have for you for your homework. I'm actually going to have you look up the name logarithmic. It does come from 2 Greek words. I'll give you a hint with that. And going back to one of our prior lessons, okay, the person that coined this term was a mathematician, John Napier. Okay, he's the one that coined the term logarithmic. So again, that's going to be something I want you to kind of look on your own, and then we'll talk about tomorrow where it came from. So this, I just rewrote it like this. Okay. Now, why the change? So here's the deal. Okay. I'm going to put this over here. So some notes about this, of how we can read this. So given y equals log b to the x. The value y is the exponent, underlying that, to which b must be raised to obtain x. Okay? Now this will make more sense when we actually put an example underneath it. We're going to see a bunch of examples today. So in other words, looking at this guy over here, okay, what does this, whatever the number is, 4, 5, 6, have to get raised to get this number? Okay, so that's what this is. Let me just put this right here. That's the exponent part. Okay, so what exponent does b have to get raised to get x? Okay. Now, the value y is called the logarithm. B is called the base. And x is called the argument. Okay, so we do have specific names for this function right here. So y is the actual log part, b is the base, and x we just call it the argument, which is nice. I think a lot of times when we look at a problem, we need to know how to state what we're looking at specifically, so having names like this can help with that. Okay? The equations, y equals log b to the x, and b to the y equals x, both define the same relationship between x and y. Y equals log b to the x is the logarithmic form, and b to the y equals x is called the exponential form. So they are equivalent, okay? So if you see something, let me box this out here. So these two mean the exact same thing, okay? In fact, when we start evaluating these, we're going to be using the exponential form to actually figure out what's going to happen over here, okay? All right. So that's the end of the notes. Not notes here, but just for this section. Any questions on what I just covered? So let's just go back through what we were doing. So at the original stage here, I was talking about, okay, what exponent do you raise to get to this guy? And over here, we didn't know. So we had to find the inverse. So what undoes this to find the x? So we found the equation, okay? We just solved for, just switch these out, got to this point. This is going to be our inverse to help us find those types of answers, okay? And we'll get to how we're solving that a little bit later. But for right now, this is our inverse. We rewrote this as this, okay? So y is our exponent that we raise b to get to our argument, which we call x. All right? Let's try some examples. Got some space down here. So we're going to write each equation in exponential form. So there's our three examples there. I'll use a different color to write the answers in. So these aren't even really problems. All I want to do is take those log expressions and convert them to the exponential, so we can see it a little bit easier. Like, what is that actually telling me? Okay, that's what we're going to do. So looking at part A, okay, so looking at the exponential, b is the base. So what was our base in this it's going to be a 3. Okay. Y is the exponent. Okay, so that's going to be 3 over here. And then the argument is what it's equal to. So 3 to the third equals 27. So that's what that logarithm is telling us. So what power do I raise 3 to get 27? The answer is 3. That's how you read it. Okay, over here, same thing. So 10 is my base. The exponent is what's over here, so that's a negative 3. And then the argument is what it's equal to, so 1 over 1,000. Okay, so 10 to the third to the negative 3 does give you 1 over 1,000. And then the last one over here, our base is 8. Our exponent is 0. So when I simplify, it should equal my argument, which is 1. Okay? Any questions on that? So far, so good? So what you have to try to keep in your mind is this. What a log is equal to is the exponent. Okay? That's what we're raising the base to. Questions? All right, let's go in the other order. When we need the exponential, can we write the log? Write each equation in logarithmic form. I guess you could say we're kind of going backwards. So for part A, let me just circle the exponent. So the exponent's 6, right? So that's what my log is going to be equal to. It has to be equal to 6. Okay? So my base is still going to be 2. No matter what, if you look at your equivalency over here, B as the base doesn't change at all in terms of where it's located. It's still going to be on that side. So looking at this, this is going to be, well, we'll use purple. Can I switch these in my hand? Yes, I can. Okay. Log 2 to the 64 would be, oops, 6. There we go. So again, this is the exponent we raise our base to get to the argument. Okay, so let's look at B. So again, there's my exponent, so it's going to be equal to that. That's my base, so base 10, and the argument's 100. So again, 10 raised to the second power gives me that 100. Over here, again, my exponent is going to be by itself. That's what it's going to be equal to. And then we have log. The base is a third. So if I raise this to the negative 1 power, I get 3. Okay? All right. Any questions on going back and forth between those two forms? So far, so good. All right. Got your goal. Let's keep going. Equivalence property of exponential expressions. Okay. If b, x, and y are real numbers, with b being positive, and it's not 1, then b to the x equals b to the y. Implies that x equals y. Okay? So for an example, I'll put it right next to it. It's kind of obvious, but if I had 2 to the third equals, well, 2 to the x, okay, what makes these guys equivalent? Well, wouldn't x just have to be 3, right? So as long as the bases are the same, the exponents have to be equal to each other for that equivalence to work. Let's look at some examples. So log, okay, base 8 to the 64 equals what? B. Log base 4 to the 1/16 equals what? And then log base third 27 equals what? Okay. Now, if you want to, and this is what I would recommend, if you look back at our definition, we have that it's equal to y. So what I would probably do is just set it equal to y, just to get used to those expressions, okay? Make it easier. Now, how do we solve these? Well, let's go back to this guy. We know that this is the same as this. So my first step to solving them is let's rewrite it using the exponential form of it. So this is going to be a to the y equals 64. Now this is a very straightforward one. What does y have to be in this case?
2.
Just 2, right? Okay. Now, if you have a case where maybe it's not as obvious, okay, how can we get to that a little quicker? Well, we can use this guy up here, okay? Can I make these the same base? Absolutely. So what I could do, just to show you another way, 64 can be rewritten as 8 squared. Okay, now they got the same base, so the exponents have to be equal, so y must be 2. It seems kind of silly because, again, that's not a difficult problem there. But if you do get something that might be a little bit more difficult, it's easier to find the same base first and then set the equations equal to each other. Okay, over here I can do the same thing. So 4 to the y equals 1 over 16. I'm going to rewrite 1 over 16 as a base of 4. So this would be 4 to the y equals 4 to the negative 2. And because they have the same base, I can set the exponents equal to each other, so we get y to be negative 2. Now, because this is not too difficult, you could probably say immediately it has to be negative 2. But again, if you need to break it apart further, please do. Okay, over here we have 1/3 raised to the y power equals 27. So again, what I can do is change that to have the same sort of base. So we could do 1/3 raised to the y equals 3 to the 3rd. Okay. And then we could say that, looking at it, this could be changed to 3 space to the negative 1 raised to the y power equals 3 to the 3rd. Okay, I'm going to bring it up here. So we get 3 to the negative y equals 3 to the 3rd. And we can see that y would have to be at negative 3 for that to work. Okay? Now again, that took a little bit more work because I had to use the properties of exponents to get to that point where they had the same base. But looking at this, some of you might see there and say, well, to be a fraction, it had to be negative, so if I make another negative, it's going to flip it. And then 3 to what power gives me 27 has to be. So you can logically figure that out. But again, it's just as good to find a similar base and set the exponents equal to each other. Okay? Any questions on how to do this? All right. Let's keep going. Some other facts, some definitions to go through. Okay, first, the log function with a base of 10 is called the common logarithmic function. Okay? So if you see something with base 10, they call it the common log. Okay? The common log function is denoted by y equals log and then x. Okay? Now notice, I didn't write the base 10 to it, right? So if you don't see a base here, you're going to assume it's 10. Okay? So just keep that in mind. All right, next, let's bring back e. The log function base e is called the natural logarithmic function. Okay? And we have a different notation for that. Okay, so here's the notation. So the natural log function is denoted by y equals ln x. Okay? That is y equals log base e to the x is written as y equals ln of x. Okay? Now, L's are kind of hard to write down in mathematics just because it looks like a 1. So a lot of times we do like a cursive L when it comes to those. Okay? All right. So any questions on just those couple facts over there? So again, if you don't see a base for this guy, you're going to assume it's 10. Okay? And if you see an ln, they're talking about a base of e. Okay, so that's our natural log function. Now, why do we call base 10 a common log function? Because a lot of our stuff is in base 10. Think about it. Think of our number system. Think about when you guys, those who are taking chemistry, you have a lot of things in base 10 with scientific notations and stuff, okay? And we'll talk about that a little bit with the application as well. Let's jump to some examples. Evaluate. Right, too big. I'm not gonna be able to fit all these. There we go. Okay. So I got 4 examples there, and we're going to evaluate these. By the way, okay, later on, hopefully before we leave today, I'm going to show you how to access that stuff on your calculator, okay? The nice part is the log button literally says log on it, okay? And the E button is something you have to access by hitting the second function, or the second button on the calculator. So again, we will get the opportunity to look at that towards the end. So for the first one, what I'm going to do is use the exponential to figure this out. Now notice there's no number here, right? So we're going to assume it's a base 10, okay? So if I set that equal to y, it's 10 to the y equals 1,000, okay? And again, if you want to come up with similar bases, I mean, you can probably guess what the number is anyway. It would be 10 to the y equals 10 to the third, therefore y equals 3, and you're done, okay? But again, if you can probably get to that conclusion a little faster, that's okay. Okay, next one. Now again, there's no base number, so we're going to assume that's the common log. So I'm going to put equals y there. So 10 to the y equals 0.01. Okay. So far so good with that. And again, could you figure out that y would have to be a -1 there? Yeah, but you can still write as similar bases here. So therefore y is equal to -1. So 1/10 or 0.1 there. So far so good? Yeah. Okay, now this guy, we already know it's different, but it has a base of e, and notice e's not written there, okay? So we have to know that ahead of time. So it'd be e to the y equals e squared. Well, this one's even simpler, huh? So that has to be a 2. And then for the last one, well, can I fit it? We're gonna try. Equals y. Okay, so again, the base is e, even though we don't write it. If we see that notation, we know that for sure. So it'd be e to the y equals 1 over e to the third. Because it's written like this, we know it must be e to the negative 3 to get to that point. So therefore, y must equal negative 3. Okay. All right. So far, so good. Yeah. Any questions? Now that we kind of have a feel for what a log looks like and how to crunch some numbers with some log stuff, let's talk about some properties with it. And we're not going to go through every single property. There's more in the next lesson, but here's some basic properties just to get us started. So basic properties of logs. Okay, first property. And we've already seen this over here, actually. I think, was it over here? No, must have erased it. Okay, but if the exponent's 0, anything raised to 0 power gives you a 1 there, because that's your first property. So that was not too bad. We kind of know that one ahead of time. Okay, log base b to the b is 1. So what do you raise b to get the same thing? It's 1. And I'm not one to memorize these properties. Like, to me, you can pretty much figure that out when you solve it, right? You see that. Okay, third property. Log b of b to the x equals x. Okay, so again, what do you raise b to get b to the x? Well, you have to raise it to x for that to work. Okay, and 4, I can fit this down here, I think. Okay, b raised to the log b of x equals x. Now, that one's a little weird. Now remember what I said, that those are inverses of each other? They undo each other, right? So you're gonna get the actual exponent here, which is x. But here's what I'm gonna do. Let me give you like a small example next to it. Because again, this one I don't think is as clear just looking at the rule. If I had something like this, 3 to the log of 3 to the 9, okay? If I had something like this. Now let's think about something. 3 to what power gives me 9? 2, right? So this could be rewritten as 3 squared, which is 9. So did this equal 9? Did we have the same base, so therefore it was just equal to this? Yeah. Okay. So that's what this property is stating for you right there. So as long as, this is the important part, maybe you want to circle it, they have to have same bases there. Okay? If those are not the same, then it's not equal to x. It doesn't work. So again, just a little small example to throw next to it. Because these are the same, my outcome ended up being 9, but I got there with a little intermediate step because that's 2, hence 3 squared gives you 9. Okay? Which helps, because here's the deal. If I have variables up here, if I don't know what the variables are, you still have to figure out what it's equal to, which is equal to the argument. All right. We're doing good. Questions so far? Still following along? Awesome. All right, let's keep going. Another example. Simplify. Another 4 examples, and this is a little different than what these 4 were like. Okay, I'm actually going to use these properties to figure out what these solutions are a little bit quicker, okay? But could you, again, could you rewrite it as an exponential to solve it? Absolutely. But for right now, let's just practice using those 4 properties, okay? So for part A, that looks like property number 2, right? We can see that these 2 are equal to each other. The base and the argument are the same. So without really doing much work, I know the answer has to be 1. But again, could you do this? 15 to the y equals 15. Y equals 1. Yeah, but if you know the property, you can get there a little quicker. Okay, over here, this is still a base of e, right? So even though we don't write it, it's still there. So if the base is equal to the argument, I think that's property 2 again. So this is just going to equal whatever the, not property 2, I'm sorry, property 3 I meant to say. So this is equal to the base, so therefore it's just the exponent itself. So it's just going to be equal to 4. So let's put this underneath what each one was. So this was property 2. This was property 3. All right. Now, this guy, that looks like the first property, right? Okay. So if this is just its base, the argument's 1, then the whole thing has to be 0, which makes sense. 50 to the 0 power is 1. So this will be property 1. And the last one, I'll put the equal sign there. I'm always running out of space. It's the fourth property. Okay, we have the same base for the log up here and just for the exponential down here. So it's just going to be equal to the argument here, which is just a plus c. So that would be property 4. All right. Any questions? Yes. Yeah, absolutely. All right. Let's look at some graphing. Okay, so we're going to dive into the graphing. Now, the good news is because we know that there's an exponential component to this, we can graph these a little bit easier that way. Okay? So let me write some notes down for that. So since y equals log base bx is the inverse of y equals b of the x, then their graphs must be symmetric with respect to the line y equals x. Okay? So just like we saw with inverses in the past, so since these are inverses of each other, then they must be symmetric to that line y equals x. Okay? So let's just draw a little generic graph underneath it. So there's y equals x. Okay? Exponential, we know what that looks like. So it looks like something like this. So my log is going to look something like this. Okay? So we just put little notes here. So this is y equals b of the x. Here's y equals log base b of the x. Okay? So that's what the graphs look like, which is pretty cool. Kind of when you turn your head, I mean, I just see like a base here and a base up here. It looks like a nice platter in a way, and then that's just like the stem of it. I don't know. That's just where my mind leads to for that one. Now, let's look at some different things with bases with logs. So I'm going to leave that there. Let me add some more graphing stuff over here. So we can also have something that looks like this. Okay. So for this one over here, let's add one little note to that graph. Okay. So this is when b is greater than 1. Okay. Looks like this. If b is a fraction, it's going to go the other direction, right? It's going to go this way. So let's talk about when b is a fraction, what those graphs look like. Okay. So when b is a fraction, we get something that looks like this. So this would be y is b of the x, where b is between 0 and 1. There's my y equals x line. Okay, so now my log function looks like this. Okay. So it messes with your mind. So you can see that this part's down here and this part's over here. Okay, so that's what those two graphs look like when you have a fractional component as your base. Let's put some solid examples underneath. I mean, it's good to have the generic form, but let's say you were tasked with graphing these. Like, how would you do it? Okay, and it's not hard. I'll show you what we have to do. It's actually pretty easy. So let's say you were tasked with graphing y equals log base 3 dx. so what would you do? Well, we're going to use the fact that these are inverses, okay? So I'm going to write an xy table with the exponential form of this, okay? So this is actually y equals 3 to the n's, okay? That's what it looks like before we do even the log stuff. And usually, you'll see it in the homework too. I start with -3 all the way to +3. That's a good spread of x values to use. You don't have to go too crazy with it. And what I'm going to do is plug each one of these into here and get the output. Okay, and here's what the output looks like. There we go. Okay. Again, I'm just plugging that number in for x and simplifying. Now, how do I obtain the log form of this? Well, because they're inverses, we just gotta switch the x and y's, right? Okay, so here's my new xy table. This one will have the log stuff. Okay, and I'll put a little note here. So you're gonna switch the x with the y, okay? Because again, that's what inverses do. When you're symmetric across the line, y equals x, you're just flipping things. So this is all it's gonna look like. So that's literally what I did. I just flipped them around. That's my XY table for this graph now. So sketching a small graph next to it. Now notice that the -3, -2, -1, so that corresponds with very small x values, okay? So let's see if I can, I'll try my best. This is a hand-drawn graph. So at 0.4, we have -3, so very close to the y-axis there. 0.11 at -2, so we're slightly farther out, but not much. 0.33, same thing. We're slightly out, but not too far. At 1, we're at 0. At 3, we're at 1. So here's 3, here's 1. And then the rest of them are a little bit too big for my graph here, but we'll go ahead and sketch a little. And we get something like that. Okay, so there we go. Alrighty. Any questions on that? So if you're tasked, which you will be, shouldn't be an if, but you will be. Okay, you take this guy, okay, graph it with its exponential, what it would look like. And then to get the log version of it, switch your x, y values for your table, and then graph it for you. Okay? Questions on that? That's your steps. Now, can we do transformations with it? Oh, you bet you can. Let's do one. Okay. So let's talk about transformations of a log function. Okay. And here's the good news. It follows what we've done before, transformations. Okay. So I'm going to write down what they are, but we know these already. Want to write those down, you can. Put it this way, if it's inside the log function, we know there has to be some sort of horizontal shift, so left and right. If the number's on the outside of the log, it's shifting it either up or down. And if the number out in front is a number bigger than 1, it's a vertical stretch. And if it's between 0 and 1, then we know that has to be a vertical shrink or vertical compression. Okay, so that's the good news, is that these transformations still follow with what we've done in the past. So let's try one out. Okay. Put this right over here. I'm going to use that exact same method. I'm going to graph the exponential. Well, not graph the exponential, but do an XY table with it. And then flip them. So graph the function. Identify the VA. And write the domain in interval notation. Okay. So here's our function. H of x equals log 2 x minus 1 plus 2. Okay. Now I'm going to list the transformations next to it. Bless you. So this is going to move to the right 1 and up 2. Okay. So that's what it's going to look like. Now, what I'm going to do, looking at this, the parent function would just be this. Right? Without the transformations, there's my parent function. So let's see if we can't make an XY table with the parent function. And then once we have that XY table with the parent function, let's include these to finish it. And then we can graph it fully. And that's going to help us find the rest of this stuff. Okay? So here we go. So first, okay, we're going to create a nice little XY table here. So let's start, let's see. Now, one thing to note, I probably should have noted this before, so my apologies. Look at the graph I did over there. Do you see how it didn't have any negative numbers, right? When I say negatives, I mean your domains. Like none of these negative numbers existed, right? They weren't there at all, okay? So this is like your vertical asymptote is what this is, okay? So it's not gonna go past here. So when I'm shifting this over 1 to the right, it's going to move that vertical asymptote a little bit over, right? It's going to shift it over 1 right. Okay, so you want to keep that in mind. So because it's shifting over to the right 1, then I'm probably not going to start with what, -3 to 3. So instead, I'll do this. I'll just stick with 2. Okay? And then this will just be y equals to the x. Okay. Now just plug those numbers in. So we get 0.25, 0.5, then we get 1, and then we get 2, and then we get 4. So now, to get my log table, I'm going to switch these. Just like that. And that's, honestly, that's the process you're going to do every single time to graph this. Now that I have this table, I don't want to graph those yet because we have these transformations to consider, okay? So if I'm going to go right 1, that means all my x values, I'm going to, add 1 to it? Does that make sense? And then here, if I'm going to go up 2, I'm going to take my y values and add 2 to each one. So using, I'll put here, using the transformations, our points will be, okay, so let me rewrite those points now using the transformations, okay? So this is going to be 1.25, and I'm going to add 2 to this, so 0. Okay, so that's where it's going to hit the x-axis at. Okay, my next point, I'm going to add 1 to this, so it'll be 1.5, add 2 to this, so that's going to be a 1. And then we just kind of continue with the rest of it. So 2, 2, and 5, 4. So those are going to be my points to graph. So before I graph anything, questions on how I went from here to here. I know, it's kind of like a long process to graph it, but it's not difficult. It just takes a little time. So again, XY table with the exponential, flip them over to get the log table, And then if you have transformations, not all the time, but if you do, use the transformations to manipulate those points a little further. Okay? So graphing it, I'll put it over here. Now because we're moving over one to the right, there's my asymptote. Okay, so it's not going to go anywhere beyond that. And graphing those points, we get something that looks like this. Okay? So there we go. It's hard to do with a hand-drawn graph. You guys are actually going to have grids that you can plot these points with. So for me, I'm just doing a really quick sketch. But these are the points you would use to sketch those. Okay? All right. Now, let's look at the other questions. So you know what the VA is. So my vertical asymptote is going to be at 1. Okay, so that's x equals 1. Put columns there. Okay, so there's that guy. Now, they also want to know the domain of this. Now let's think about domains just real quick. Okay? Inside here, that can never be negative. It can never be 0. Okay, well, why is that the case? Well, think about it. If I had something like this, okay, we know that this means 2 to the third equals 8. Okay? Does this side ever give me a negative number over here? Could that ever happen? No. Okay? Could this ever give me a 0? Can I raise anything to a power and get 0? No, it's never going to happen. So the argument helps me find my domain. Okay? So it cannot be 0, but it has to be greater than 0 because it can't be negative. So to find your domain, and I apologize, this looks like a mess. I'm going to put it on this whiteboard, okay? I mean, for you guys, you could do it neatly in your notes. So my domain is going to take my argument, which is x minus 1, and make it greater than 0 and solve for it, okay? So looking at this, just x has to be greater than 1. So my domain is just going to be 1 to negative infinity. Okay, but again, it just comes down to why is that the case? Because, again, nothing on this side could I raise to get a 0 here, or negative. So that's why we have to set it greater than to 0. All right. Any questions? Okay, so that's graphing. Okay, I got 2 more examples and we're done. Oh, well. Use the wrong marker color. Identify the domain of the log function. Okay, and what we'll do, we'll just do one example for this one. I have 2 here, but we'll just do the 1. Okay, so let's say this is my function, and I want to know what the domain is going to be. Okay, what x values am I allowed to plug in? Keeping in mind that this can't be 0, and it can't be negative, right? Okay, so let's just put a note here. We want our argument to be greater than 0. So therefore, we get x squared minus 16 is greater than 0. Now, this should look familiar because we've done this in the past. So what I'm going to do is find out when is this equal to 0. That's going to be my boundary points, and I'm going to test points out to see what x values makes this bigger than 0, okay? So for this one, it's actually kind of easy. So let's set it equal to 0 and solve. So if I add 16, take the square root, we have 4 and negative 4. So let me go ahead and draw a little generic number line, 4, negative 4. I'm going to test points out. So here I'll test negative 5, in the middle I'll test 0, and over here I'll test 5. And again, the goal is to see when is this bigger than 0. Not equal to it, just bigger to it. Okay? So we can do a little sign table. Okay. I know some people would rather just plug the number in and see if it works. You know, is the number positive or negative? You could do that. I'm not going to stop you. Okay. For me, I like the sign tables. It's kind of nice. So if I plug -5 in, okay, I get negative, negative, and when you multiply those, you get positive. If I plug 0 in, I get negative, positive. Multiply them together, you get a negative. If I plug 5 in, they both become positive, and when multiplied, I get positive. Okay? So it looks like we have two intervals that work, okay, that make that inequality greater than 0. So my domain, and this is why I kind of like graphing this. I'm going to shade that part in. So I got to find an interval with that shaded part and an interval with the other shaded part. So that's going to be from -infinity to -5, union with 5 to infinity. Oh, not 5s. Oh my gosh. 4s. Sorry. I saw the 5s there and immediately look at 5s. No, those are 4s. There we go. And again, we're not including it because we don't want it to be 0. An argument equal to 0 doesn't make sense when it comes to the exponential part. All right. Questions? All right, let's try an application, and then we're done. Now, one thing to note, so a good reason as to why we do this. I'm going to write it over here. If I had these numbers, 10, 100, 1,000, 10,000, and so forth, if I follow that trend, my number is going to get bigger and bigger, right? Well, if I take base 10 log to all these numbers, they become 1, 2, 3, 4, and so forth. So when our numbers get larger in mathematics, sometimes we'll take the log of those numbers, in this case a base 10, log of base 10, and the outputs, those numbers are easier to work with, right? They're a lot smaller, okay? So one of the reasons why we use log is just to make some of these numbers a lot smaller to work with. So here's one way. Let's talk about earthquakes. So the intensity, which we're going to call I, of an earthquake is measured by a seismograph. Man, I cannot talk. I sub O is a minimum reference intensity of a 0 level earthquake against which the intensities of other earthquakes may be compared. Okay, so the formula for this is m equals log the intensity you're looking at over the intensity it's compared to. Okay, now notice there's no base to this, so we're looking at a base 10, right? Okay, so this is a common log problem. So the intensity of the earthquake you're looking at now over the reference that you're using for it. So for part A's question, okay, it says here, determine the magnitude of an earthquake that is 10 to the 2.2 power times the initial quake. Okay. So we're going to use that formula to do so. So it's 10 to the 2.2 power times the initial. So this is going to be m equals log. So this is 10 to the 2.2 power times the initial over the initial. I use initial because that's always what we use. Like anything that's sub-zero, it's minimal. I should be saying minimum over the minimum intensity. I don't know what the minimum intensity is, but the good news is, don't they cancel out? Whatever it is, it cancels out. This problem didn't give me it. So therefore, m is equal to the log of just 10 to the 2.2 power. Now again, because this is a base 10, if you look at it, it'd be 10 to the same base raised to the exponent. Is that property 3? I can't quite remember which property it was. So this is just going to be 2.2. So it's 2.2 times in tenths. Okay. All right. Let's try next one. Part B, determine the magnitude that is 10 to the 1.3 times the minimum. Okay, and again, they don't tell me the minimum, and you might have that. In your problem, they actually might give you the minimum to where you don't have to worry about canceling out the isomos. You might just actually have to divide the two to get to that point. But in this case, we're not given any initial there. So m is equal to log, same principle, 1.3 times the minimum over the minimum. Okay. So that's just log the, whoa, went right out of my hand. The minimums cancel out, that's just 10 to the 1.3. And because it is a base 10, using that property, it's only 1.3 times as a tenth of. So for my final question is, how many times, if the bell does ring, you might have to hold 2 more minutes. I'm right at the end here. So how many times more intense is a 2.2 magnitude earthquake than a 1.3? Okay, well, all we gotta do is just use the actual powers here. So the intensity, okay, how many more times intense it is, so it'd be 10 to the 2.2 over 10 to the 1.3, oops. Okay, knowing our basic exponential rules, you just subtract the exponents. So it's 10 to the 0.9, which is roughly 7.9 times more intense. So again, the reason why logs help us a lot is that instead of working with numbers that, I mean, this isn't as large of a number, but if you had 10 to the 50th power, then yeah, you kind of want to mess with some smaller values. So using base 10 logs can help chop that down. I'll find the marker calculator.